Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. Today we are joined by Dr. Tulsi Patel to discuss AFRL's literary group, LitWISE, nanoelectronics, and how art can influence science in incredible ways.
In 3, 2, 1.
Dr. Patel, welcome to the podcast.
Thank you so much. I'm so excited to be here.
We're super excited to have you as well. Now, right now, you are a postdoctoral fellow at AFRL through the National Research Council, or NRC. And by training, you're a materials engineer. And we're going to talk about your career, and we're going to use a lot of book analogies throughout our podcast. So we're going to crack open the book about your career and your life and what got you excited about STEM in the first place.
Yeah, so I really loved math and chemistry in high school. So the natural progression there was to choose chemical engineering for undergrad. But at the same time, I read a book on global warming, which really inspired me. Actually, the name of the book was called The Global Warming Survival Handbook. And one part of that book was on energy. And that part really resonated with me. My parents emigrated from India. I was born and raised here in Connecticut. And I was constantly reminded of the scarcity of water and food and electricity in other parts of the world. And, this was how I was going to make it a better world. But, it didn't really hit me until I lived abroad. I had the privilege to live in Italy and in Korea. And you're limited in your power consumption there. For example, I lived a whole year in Italy and a whole summer in Korea without a dryer. And laundry day was very onerous in my opinion, but just those little things, we realized that here in the US, there's so much energy availability in other parts of the world. Even if it's not a third world country, it's still limited in some ways. But so we have 7 billion people on this planet right now. And I believe it is our duty as one of the most prosperous countries in this world to provide all of humanity a means to thrive, which requires meeting energy demands through clean energy breakthroughs and, of course, transformational policies. So getting governments to commit to protecting the planet.
And what's interesting about this too is that it could drive you from such a young age. So I'm curious, along your journey, we're going to kind of build up towards your undergraduate. Did this guide any of the classes you took in high school? Like you're looking for more environmental sciences, things like that?
We weren't really offered those types of classes. I took all the AP sciences, math, of course, English, because I loved reading. But I think it was really in undergrad where I got to explore that more. I concentrated in environmental engineering, which I got to learn about clean water, clean air, and how those things affect our daily lives. I had 3 wonderful opportunities to do research as an undergrad. My first experience was at Penn State through our research experience for undergraduates program. It's an NSF program where I did quantum mechanical modeling called density functional theory, DFT, of lithium sulfur batteries. So I went into the experience. I was a sophomore. I just graduated and I knew nothing about Schrodinger equation or wave particle duality, all these basic concepts of quantum mechanics. And those concepts are so important to understanding a lot of these research endeavors. Quantum mechanics specifically describes physical properties, the interactions at the atomic and subatomic level.
So you can actually use or potentially use quantum mechanics to influence energy or storage or batteries. What is like the end goal of this study?
So the cathode in the lithium sulfur batteries was magnesium oxide. And you can dope it with different materials, different atoms, and change the properties. And that's at the quantum level. So at the atomic level that you're changing these properties, and it influences basically how the device works. And mind you, I took quantum mechanics in Italy 2 years later in Italian. So it was a whole other level of quantum I had to learn. But it's been so crucial to actually almost any research project I've done since.
Well, having that worldly view had to be super cool, though. I imagine getting the chance to be educated in Italy, and like you said, even living in Korea. Did this push any boundaries or open your mind to different outcomes here that you may not have reached in the U.S.? Like, what kind of like findings, I should say, did you get from a more worldly education?
Yeah, I had a unique opportunity to be selected and participate in a master's exchange program between Politecnico di Milano and University of Connecticut, which focused on energy sustainability. So besides being immersed in this incredible Italian culture, some of the things I observed were equal presence of men and women in my classes and also the research group. At UConn, there's 8 women in a class of 50, 60, and then I was the only female in 2 out of the 3 research groups. So that really broadened my perspective on gender equity in the sciences. Additionally, in lieu of written exams, we had one final oral exam for each class, which you didn't necessarily pass the first time or the next couple times either. So this really taught me attention to detail and really being able to remember these concepts and applying it to complex research problems. And then finally, this experience taught me the intersection of art and science and how much the Italians valued it. I just recall there was a discussion on colors and shapes of photovoltaics that would be integrated into windows. It's really hard to control those things when you're building a device, but the art department was really interested in the aesthetics of integrating science into everyday life. We, of course, have a term for this now. It's called STEAM, science, technology, and engineering, art, and mathematics. But that concept 10 years ago was incredibly new for me.
And I'm curious then, so with this education, with especially adding the art of science, what does that really mean to you, especially learning in Italy? Like what makes the confluence work together? Many people, until STEAM was really established, just called it STEM. So how does art fit in?
I think just from a young age, you're taught to appreciate the arts equally to the sciences, which maybe it's not as true here. I mean, of course, I love music and movies, but people don't appreciate the arts as much. And Italy has so much of a history in the Renaissance that it's very integrated into their lives. Right? They have to know Dante's Inferno, inside and out, as well as learning these very difficult topics in engineering. So being well-rounded in Italy is just a way of life. Whereas here, you are good at one thing or the other, and that's where your focus is.
Yeah, and that's something really beautiful to touch on. Because I mean, thinking about Dante Alighieri and others, like I visited the tower when I was in Florence. I mean, it's so cool to think about how these stories, many people who were doing research, especially in the Italian Renaissance, were artists or artisans. So it's the idea of like, okay, I'm going to mix a new type of paint, or I'm going to be making this beautiful sculpture, or furthering that, I'm going to write a story that makes commentary and can drive people to try to solve other issues. There really was, I mean, there was a marriage of both. It really wasn't separate in many ways. And that's something I think a lot of people today can really enjoy more. It's like, hey, if you dive into this and maybe approach it from an artist angle, you may see something that maybe a clerical, clear-cut engineering way could have missed, and you need both. So I agree, having even a more well-rounded view can really change the way you approach any problem.
Right. And you think about Leonardo da Vinci and his approach, right? I mean, he knew how to bring the two together, and he was both a brilliant scientist and an artist.
So something we'd be remiss to touch on is with all of your studies, the amazing work you did internationally, you had a passion for photovoltaic cells. Can you talk about what those are exactly and how they tied into your studies?
Yeah, so in undergrad, I had an opportunity one summer to work on dye-sensitized solar cells. In these solar cells, you have a semiconductor. In my case, it was titania, TiO2, which is in everything from our powdered donuts to white paint. Anything white has titania in it. And that semiconductor was coated with some sort of dye. And so photons would hit the dye, electron would be transferred into the semiconductor, and it would essentially create a current. So a basic concept of a solar cell is that sunlight, more specifically photons in the UV, visible, and near IR, can create direct current in a class of materials called semiconductors. When you add an impurity atom called a dopant to a semiconductor, we can create excess holes on one side and excess electrons on the other side. and then create what is called a p-n junction. One ubiquitous semiconductor material is called silicon. So there are, of course, many types of materials used for solar cells, including titania for dye-sensitized solar cells, which was the topic of my master's dissertation in Italy.
Well, it sounds like there's a lot of moving parts to make it work, but when they're all working together, then as actually produced, it should take the energy of the sun, give it to us for energy. So, I mean, it's I didn't realize how many steps or parts went into it too. So, were your studies looking how it worked or how to improve it?
Yeah, so it was very material science-based research project. So it was focused on creating the titania semiconductor and creating more surface area. So we want the dye to be in more areas. So we have more photons hitting that dye and the electron being transferred into the semiconductor and of course coming out. So really optimizing the hierarchy of how the semiconductor is grown.
So you did some great research at Penn State and UConn. Sounds like you had an amazing experience at grad school in Italy. So after those final exams in Italy, how did you end up at AFRL?
So I'll backtrack a little bit. After my master's, I decided to stay at UConn for my PhD. Ended up staying for 10 years between my bachelor's, master's, and PhD. For the PhD, I actually pivoted to a new topic of the time, multi-material additive manufacturing of ceramics and metals, specifically ferroelectric oxides and aerospace alloys. And the goal here was to integrate the functionality into aerospace components. So we can have sensors and actuators and solid state heating and cooling. And I mean, it's very challenging when you're bringing a metal and a ceramic together at a high temperature. So there are some of the challenges associated with that project. But post-graduation, I knew I wanted to go to a government laboratory. To be honest, I really was interested in NIST and their efforts on additive manufacturing. It's also closer to home, to Connecticut. I would have to say AFRL was not on my radar until my PhD co-advisor, Pamira Alpay, introduced me to Tim Bunning, who was the chief scientist of the Materials and Manufacturing Directorate at the time. So Tim invited me to give a talk. This was March of 2018. I went, not really expecting much, but after my visit, I was pleasantly surprised at how much I liked the people and the laboratory and the mission. I ultimately decided to apply for the NRC postdoctoral fellowship at AFRL, was accepted, and I have been here since February of 2019.
Beautiful. And with that, if people are keeping track here, we're now in chapter 5. So as chapter 5 opens up, we're curious then. So what have you been doing currently at the Materials Manufacturing Directorate? So what's your mission been and how has it kind of evolved?
Yeah, so the first 3 years of my NRC, I worked in the composites branch on structural ceramics and composites, specifically ceramic matrix composites. These materials are used in extreme environments such as turbine engines and hypersonic platforms. A couple months ago, I switched to the nanoelectronic materials branch and have been contributing to the NeuroPipe ARAP project. So this effort is to enhance and accelerate DoD's capabilities and emerging neuromorphic hardware elements, essentially to develop a set of novel integrated circuit chips for neuromorphic computing tasks, which incorporate emerging set of materials and devices that are being developed at the lab.
So there's another part of this conversation that I'm curious with. So neuromorphic computing. I'm curious for a lot of our listeners here. So what is it exactly and how long have we been studying it? Because it sounds, at least in my mind, pretty new.
Yeah, so the concept of neuromorphic computing has been around for a long time. Neuromorphic computing consists of electronic components that emulate processes of neurons and synapses in the brain. So quite complex, right? And you also need very complex materials to be able to do those computing tasks. So at this stage, we have those materials, and this is an area that I've been working on characterizing those materials to really understand the phenomena at the nanoscale level.
So you're leveraging materials to try to make computing mimic our brain, because like our brains are like the ultimate computer, basically.
Yes, that's exactly what people are trying to do.
Well, I think that's a good idea. So, I mean, I love that. So I'd heard it mentioning before, but you really broke that down in an easy to follow way. So kind of furthering a lot of that technical work, are there other research projects or angles your team has taken over the years that you can share with us?
Yeah, so for the past 3+ years, I've been primarily using a characterization tool called electron microscopy to study materials. My current project entails high resolution transmission electron microscopy, TEM. So you use electrons to look at very, very thin slabs of materials. And at the same time, what I'm trying to do is to heat it up in the microscope, as well as apply a voltage and see crystals growing, see domain switching in this sort of material. Specifically, I've been looking at materials for memristors, which are used for neuromorphic computing. One of the materials is called hafnium zirconium oxide, which utilizes ferroelectric tunnel junctions. So we come back to quantum mechanics. You can have a wave function that basically tunnels through a potential barrier. Essentially, this increases energy efficiency. You don't need to overcome the barrier. You can just tunnel right through it. So these films are typically 5 to 10 nanometers, incredibly thin. And I hopefully will get it to work in the near future before I leave AFRL, but I'm preparing samples to look in that microscope and be able to watch crystals grow and domain switch in real time. Very challenging problem, very difficult to do. And, even after I leave, I'm hoping my team can do it still.
So you mentioned that you actually heat these up, and you said that's through an electrical pulse then? You're actually able to heat up some of these electrons you're working with or observing?
So what happens is you have a special holder you put into the microscope with your material in it. And that material has to be incredibly thin, less than 50 nanometers. So electrons can go through the entire slab of material. And you're able to image this using some sort of CCD camera. But so this work is really fun and exciting. It requires a team of experts to grow and characterize all these devices, as well as very expensive equipment. I'm really grateful to have this opportunity to do this high impact work.
Of course. I mean, as we know, we're kind of establishing here that AFRL really has one-of-a-kind facilities for this and one-of-a-kind materials to work with, and of course, these machines that can make it possible. And something an angle I want to hit here, because the quantum world is just so much fun. But as you know, working in it, a lot of the principles of quantum mechanics do not correlate to macro mechanics. They're almost in flux and sometimes in contradiction. So how do you, is there any interesting things you have found working with that? Like, there's got to be some workarounds to make sure that the micro, or I should say quantum, works with the macro. Are there weird things you've noticed during your research? Like, hey, when I shoot a particle this way, it goes the opposite from what we think, or anything wacky like that?
Yeah, so a lot of the properties that we see at the macro level really change at the nanoscale level. So essentially, with this material that I'm working with now, we want to have a thing called negative capacitance, right? That's a very abstract term, negative capacitance. But essentially, coming back to tunneling quantum effects, you're really extracting those properties that just cannot happen at the macro level.
It is mind-bending in a way to think about that. That is just so neat. You can work in a space that's so foreign to so many people, but you are helping push the way with your team forward to better characterize it, like you mentioned. That is amazing.
Absolutely. Even with the characterization side, that's very challenging, complex problem that I'm tackling, but growing these materials are extremely difficult. And it's only possible now that we have methods to make these films at the nanoatomic level. So they're called thin film methods, and it requires vacuum sort of deposition method.
So as you work on all this research to support ultimately neuromorphic computing, what will neuromorphic computing enable us to do, or better neuromorphic computing?
Yeah, neuromorphic computing will be pivotal for autonomous and semi-autonomous vehicles, sensors, data processing platforms, and human-machine interfaces that are being envisioned and developed across DoD community. The timeline, I hope soon. We're really pushing a lot of these autonomous platforms forward. And we have the tools to not only make these sorts of devices, but characterize them, understand the phenomena, and hopefully scale it up and deploy it to society.
Well, speaking of deploying things to society and working through to future plans, part of your journey was finding a group called LitWISE, where this is a very forward-thinking, very awesome group that is a great thing to do alongside all of your studying in the quantum world. So can you kind of inform our listeners, what is LitWISE and what drew you to it?
Sure. LitWISE is a workforce development focused book club, part of the Air Force Women in Science and Engineering, AFWISE group. We meet on a monthly basis to discuss a book or an article, and it's led by various members of the AFRL community. So I joined the group in March of 2019 when I first arrived. I really enjoyed the people and the discussion, so I regularly attended the meetings. In August of 2020, the LitWISE lead at the time, Mary Shelley, she asked me if I could take over as lead, and I, of course, said yes. I would say it's been an amazing experience, really getting to use the leadership and personal development skills that I learned at LitWISE to lead LitWISE.
Did your team have any, favorite articles or books that you dove into during your tenure?
So we have discussed many genres, from women in STEM and in the workplace to leadership and personal development. I have enjoyed each and every book that we have read, and it spanned so much. And the person who is leading the discussion gets to decide what they want to discuss. But some of my favorites are The Moment a Lift, How Empowering Women Changes the World by Melinda Gates, and The Go-Giver, a little story about a powerful business idea by Bob Berg and John David Mann. I'm also happy to share the whole reading list to listeners. I really do recommend them. They're worthwhile to explore.
But again, folks, you want to stay tuned to make sure you're able to at least take part or at least read alongside Tulsi and the team. So thank you again for mentioning that and clarifying. Going along here then, so we've talked a lot about LitWISE, your awesome career, even books recommended, both the top and end here of the podcast. And as we kind of round things out here, getting towards the epilogue, I'm curious. So if there's folks who are looking to follow in the same footsteps as you, wanting to become a material scientist or even work in environmental science, do you have any recommendations or advice for them as they begin their careers, or whether that be in high school, college, or going forward?
Yeah, material science is a very broad field. So take the opportunity to learn as much as possible about different materials and their applications. I think you will slowly find out that there's so much overlap and they're so interconnected, as I'm finding out now. Second, make a plan. Have big aspirations, the bigger, the better, but don't be afraid to take a risk and fail. Life throws many curveballs, so building resiliency early is super important. And lastly, being open-minded and flexible. There are so many wonderful opportunities out there. Just don't pigeonhole yourself to one job, one location, one research area. When I was a freshman in college and wanted to save the world through renewable energy technologies, I would have never imagined myself ending up at AFRL 10 years later and working on materials for advanced computing that also contribute to the cause through high efficiency electronics. So you really don't know where life may take you. Just make every opportunity count.
Speaking of not knowing where life's going to take you, I know Ken just put this as your epilogue, but okay, if the next book in the Dr. Patel series, what are your next steps? You're just at AFRL for a bit as a postdoctoral fellow.
Yeah, I am very excited to share. In September, I will be starting as a AAAS Science and Technology Policy Fellow at OSD. I will be working in cost assessment and program evaluation, CAPE. The organization provides Secretary and the Deputy Secretary of Defense unbiased analyses on all aspects of the defense program. And I'm just super excited to join the office and make impactful contributions to DoD. hopefully in climate change and advanced computing.
Wow. Well, how exciting. And all of this ties back to that very first book that you read in high school that really triggered your interest and energy and things like that. Now it's taking you all across the world in your studies, took you to AFRL, and now it's going to take you to the Office of the Secretary of Defense. Very cool. Tulsi, thank you so much for joining us today, and we look forward to seeing where your journey takes you.
Thank you so much, Kenneth, Michelle. It has truly been a pleasure.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.